Hello children, warmly welcome to Guru Gedara educational program. Today I am going to teach you another important lesson in grade 11 science syllabus which comes under unit 11, that is electronics. What do you think about this topic? When you hear about electronics, most of the students have a doubt. How can we answer for the questions relevant to electronics? But I am sure if you watch this program continuously, all the concepts will be clear to you. Right, my dear children, you can understand what are the electronic appliances that we use in our day-to-day life. You all know that in our day-to-day life, we use various electronic appliances such as television, laptops, mobile phones. All these are the few electronic appliances that we use in our day-to-day life. Right. We use various electronic appliances to make our day-to-day tasks easier. Right. Electronic appliances consist of conductors, insulators, and semiconductors. You have heard about conductors, insulators, and semiconductors. When you think about these conductors, insulators, and semiconductors, semiconductors play a major role, right? How to classify matter into three categories as conductors, insulators, and semiconductors, right? The criterion based on this classification is the conductivity of electricity or the ability of conducting electricity through these materials, because the conductivity of electricity differ from conductors, insulators, and semiconductors. Let's learn how it differ from one material to another material. Right. Conductors. First of all, we can pay our attention on conductors. What are conductors and how do we call a particular material as a conductor? My dear children, you can focus your attention. Materials that conduct electricity well under room temperature are called as conductors. You have studied this when you were in the grade 6. Materials that conduct electricity well under room temperature are called as conductors. What are the examples for conductors? Can you remember? Right. You can watch the examples. Metals and alloys are the common examples for conductors. What are the examples for metals? Copper, gold, iron, tin, aluminium, nickel, lead, zinc, and liquid mercury. Those are the examples for metals. What are called as alloys? Alloys are mixed metals. Right. We know carat 22 gold, nichrome, which is made up of nickel and chromium, soldering, lead, brass are examples for alloys. Right. Then let's think about insulators. What are called as insulators? Have you heard about insulators? Yes, you might have. Materials which do not conduct electricity under room temperature are called as insulators. They haven't the ability to conduct electricity through them. As you can see, nonmetals are good examples for insulators. Let's see some examples for nonmetals: sulfur, phosphorus, rubber, plastic, wax, glass, rocks, papers, dried wood, ebonite, perspex are good examples for insulators or the materials which do not conduct electricity. Right. Then, have you ever heard about the graphite? Yes, graphite is one allotrope of carbon. You know, my dear children, carbon has many allotropes. Diamond, graphite, coal, charcoal, soot, all these are examples for allotropes of carbon. So, although the graphite, which is an allotrope of carbon, is a nonmetal, it conducts electricity. Why do I say so? Because earlier I told you metals and alloys are conductors, but most of the nonmetals are insulators. But here there is a special instance. Such an instance is called as incompatible instance. Why is that? Although the graphite is a nonmetal, it conducts electricity, right? Then semiconductors. What are called as semiconductors? Semi means in between conductivity and non-conductivity. Right. We can define that materials which conduct only a little amount of electricity under room temperature as semiconductors. They conduct only very small amount of electricity under room temperature. Do you know some examples for semiconductors? Yes, you may know. Metalloids are the examples for semiconductors. What are the examples for metalloids that you know? Right. Silicon and germanium are good examples for semiconductors. These elements belong to fourth group of the periodic table. Right. Then we have to understand where we apply these conductors, insulators and semiconductors in our day-to-day life. Right. These are some examples. When you think about these appliances, we use semiconductors, conductors as well as insulators. Now, how does a matter become a conductor, an insulator or a semiconductor? What do you think that? Let's learn. How does a matter become a conductor? Conductors contain huge amount of free electrons. What? Free electrons. When receiving a potential difference, these free electrons begin to flow from one side to another side. Right. You can see that. The first diagram shows you the presence of free electrons in a conductor. This consists of huge amount of free electrons. But as you can see in the second figure, when a potential difference is supplied to either side of this conductor, the free electrons available in this conductor begin to flow from one side to another side. That is because of the supplied potential difference. Right. As you can see in this diagram, free electrons flow from negative terminal to the positive terminal when supplying a potential difference. But you have to remember that the direction of current flow is opposite to the direction of flow of free electrons. Why is that? Though the free electrons flow from negative terminal to the positive terminal, conventionally electricity or electric current flows from positive terminal to the negative terminal. You can see the arrows. The blue color arrow represents the direction of electron flow, while the red color arrow represents the direction of current flow. Right. Then we studied about conductors. how does a matter become a conductor? Now let's focus our attention on insulators. How does a matter become an insulator? My dear children, there are no free electrons in insulators, and the available electrons are also tightly attracted to the nucleus. You know that electrons lie around the nucleus. Nucleus is positively charged. As a result, negatively charged free electrons are tightly attracted to the positively charged nucleus at the center of the atom. Right. Then we have to understand, how does a matter become a semiconductor? We learned so far how does a matter become a conductor, how does a matter become an insulator. Then we have to realize, how does a matter become a semiconductor? My dear children, semiconductors contain a small amount of free electrons. Now you can clarify the difference. Conductors consist of huge amount of free electrons. Insulators consist of small amount of free electrons or lack of free electrons. But semiconductors consist of small amount of free electrons. Right. Then using this video, you can realize the comparison of conductivity. As you can see, the first figure shows you a conductor, a metal copper. It shows you the flow of free electrons. Second figure shows you a metalloid, silicon, which belongs to a semiconductor. Small amount of electrons flow through that, as it is a semiconductor. When you think about the third figure, it is a non-metal glass. There is no flow of electrons, because as we learned earlier, non-metals or insulators have no free electrons. That's the difference. Then you can understand the difference among conductors, insulators, and semiconductors. All right, dear children, although we studied about conductors, insulators, and semiconductors, in this chapter we mainly focus our attention on the semiconductors. Right. Then let's learn the effect of temperature on the electrical conductivity of semiconductors. As you can see, silicon atoms form covalent bonds with the nearby silicon atoms to become a lattice. This takes place at 0 Kelvin. You know, 0 Kelvin is the lowest temperature that an object can exist. Here, each and every silicon atom forms covalent bonds, very weak covalent bonds, with nearby atoms to become a lattice. We call such a lattice as an atomic lattice, as it contains only silicon. Right. Then what happens when supplying heat, or when the silicon atom, silicon lattice receives heat? What happens? The little covalent bonds or the weak covalent bonds among the atoms may break due to the heat and release one electron from the covalent bond. Such a released free electrons is called as a free electron. When releasing a free electron, in that location a hole will be created. A hole means a lack of electron. Then you can understand this takes place on heating or above 0 Kelvin, right. Then you can understand, my dear children, breaking down of covalent bonds results free electrons and holes in semiconductors, which act as charge carriers. You can remember, in conductors, free electrons act as the charge carriers. But in semiconductors, there are two types of charge carriers as free electrons and holes. We consider free electrons as negatively charged charge carriers and holes as positively charged charge carriers. As a result, the conductivity of semiconductors increases with the temperature, right. Now, we are talking about the effect of temperature on the conductivity of semiconductors. Let's focus our attention on this simple diagram. When keeping a semiconductor between A and B at room temperature, here the green color represents a semiconductor at room temperature. What happens? If we keep this kind of semiconductor in between A and B, the brightness is low as the electrical conductivity is low at room temperature. Then, when keeping a semiconductor between A and B at a higher temperature, when the temperature is bit higher than the room temperature, then you can understand the brightness is higher than the previous instance. That means the brightness is higher as the electrical conductivity is high at high temperatures. Then what can we understand that? The conductivity of semiconductors can be increased by increasing the temperature. There is an effect of temperature on the conductivity of semiconductors. Here, when you think about a conductor, we can understand how does temperature affect on the conductivity of conductors. Here, as I told you earlier, conductors consist of large number of free electrons. But when the temperature increases, how does it affect on the conductivity of conductors? Here, when supplying heat, the metal atoms as well as the free electrons begin to vibrate. Because of this vibration of metal atoms and free electrons, a turbulence is developed by vibrating atoms and free electrons due to the gained heat energy, and that obstructs the flow of current. So, we can understand that temperature effect on semiconductors. How does it affect? When the temperature increases, conductivity of semiconductors increases, but the same temperature effect in different way on the conductors. How? When keeping a conductor between A and B at room temperature, you can see the higher brightness of the bulb. The brightness is higher as the electrical conductivity is high at room temperature because we used a conductor. Now, if we keep a conductor between A and B at a high temperature, you can see when keeping a conductor between A and B at high temperature, what happens to the brightness? Brightness decreases. The brightness is low as the electrical conductivity is low at high temperature. Then what can you understand? Even though the temperature increases the conductivity of semiconductors, the temperature decreases the conductivity of conductors. Right. We can summarize the things that we learned so far. The conductivity of semiconductors increases with the temperature, while in conductors the conductivity decreases with the temperature. Now, let us focus our attention on silicon. You know, silicon is an element belong to fourth group in the periodic table. You can see a picture of silicon. Then we can realize the atomic structure of silicon. Here, silicon, it contains 14 electrons. In the outermost shell, there are 4 electrons. Here, this is the structure of a silicon lattice. Each and every silicon atom forms little covalent bonds with nearby silicon atom. Here, through this periodic table, we can further realize the location or the exact position of the silicon in the periodic table. This is the fourth group, third period. Now, silicon, we paid much attention on silicon. How does silicon exist as a lattice? As we learned earlier, each silicon atom forms covalent bonds with 4 other surrounding silicon atoms to gain octet configuration. What is octet? You all know, you have studied when you were in the grade 10. All the atoms prefer to have 8 electrons in their outermost energy level. This is called as octet. Octet means having 8 electrons in the outermost energy level. In that instance, atoms become stable. You can watch the 3-dimensional figure of silicon and also the structure of silicon lattice. Right. Let us pay our attention on formation of free electrons and holes by breaking weak covalent bonds over heat. All right. Then we should be able to classify semiconductors into 2 categories. Do you know what are the 2 types of semiconductors? They are intrinsic semiconductors and extrinsic semiconductors. We are going to study more information about these 2 types of semiconductors in coming slides. Intrinsic semiconductors. Intrinsic semiconductors. You have heard this, right? Intrinsic semiconductors are pure semiconductors that contains only one element. Intrinsic semiconductors conduct only a little amount of electricity due to lack of free electrons and holes. Because we learned earlier, when heat is applied, the formation of holes and free electrons takes place, but there are only small amount of free electrons or holes, or we can say simply small amount of charge carriers. As they are pure semiconductors, they conduct only a little amount of electricity. This is a problem. So, we want to increase the conductivity of semiconductors by using a special manner. Before that, we can watch a video to find out the conductivity of intrinsic semiconductors. As you can see, this figure shows you intrinsic semiconductor. When heat is applied, the breaking down of bonds takes place and free electrons release or diffuse. It moves here and there within the lattice. Again, another free electron may take place. At the same time, a hole will form. Right. This is how intrinsic semiconductors form free electrons and holes. Let's move to the extrinsic semiconductors. My dear children, as I told you earlier, intrinsic semiconductors consist only a very small amount of free electrons and holes. So, scientists did various experiments and they discovered how to increase the conductivity of intrinsic semiconductors. Then they made extrinsic semiconductors. What are called as extrinsic semiconductors and how to make them? Let's learn. They are made by doping. A term we use for that is doping. What is doping then? Doping is the process of mixing small amount of other element, or we can say impurities from group 3 or group 5 in order to increase the conductivity of intrinsic semiconductors. Then semiconductors made by doping are called as extrinsic semiconductors. My dear children, can you realize the difference between intrinsic semiconductors and extrinsic semiconductors? I am sure you can identify. Extrinsic semiconductors are made by doping group 3 element or group 5 element with the pure intrinsic semiconductors in the group 4. Right. Now, I am going to show you the way of selecting elements or impurities for the process of doping. Let's focus our attention on the periodic table. You know, silicon carbon belongs to group 4, but boron aluminium belongs to group 3. Nitrogen, phosphorus, arsenic belong to group 5. Then you can see the atomic structure of boron. There are 3 electrons in the outermost shell. Atomic structure of aluminium, there are 3 electrons in the outermost shell. So, you can remember about the valency. The valency depends on the amount of electrons present in the outermost energy level. You know, valency is the ability of an atom to combine with another atom. Right. So, we call boron and aluminium as trivalent elements. Why do I say so? Because both the elements have only 3 electrons in the outermost energy level. Then let's focus our attention on the elements in group 5, nitrogen, phosphorus, arsenic. Here I have mentioned only phosphorus and arsenic. Phosphorus. Outermost energy level of the phosphorus contains 1, 2, 3, 4, 5. 5 elements, 5 electrons. Arsenic 1, 2, 3, 4, 5. 5 electrons. As a result, we call for phosphorus and arsenic as pentavalent elements. pentavalent elements. Phosphorus, aluminium, arsenic. Right. Then I told you about extrinsic semiconductors. What are the two types of extrinsic semiconductors? There are two forms as p-type semiconductors and n-type semiconductors. All right. P-type semiconductors can be made by doping group 3 elements. We can dope boron or aluminium. Here, dope in pure silicon with aluminium to form p-type semiconductors. Let's watch a video to find out the process of doping aluminium with silicon to form p-type semiconductors. You can watch. In place of silicon atom, an aluminium atom can be replaced. As you know that aluminium has only 3 electrons, as a result, in each and every instance, a hole will be formed. A hole will be formed because aluminium forms 3 covalent bonds with nearby silicon. So, one silicon atom will not be able to form a covalent bond. That means a hole will be created when doping one aluminium atom. If we dope thousands of aluminium atom, 1000 holes will be there. Millions of aluminium atom, millions of holes will be there. That means when doping group 3 aluminium or boron, a large number of holes will be there in the silicon. So, as I told you earlier, my dear children, you all know that holes represent positive charge. That means when doping aluminium with silicon, positively charged holes will be formed. That is why we call them as p-type semiconductor. Let's learn how to form n-type semiconductors. You know, n-type means negative type. N-type semiconductors can be made by doping group 5 element with the group 4 silicon. Here we can use phosphorus or arsenic. Doping pure silicon with arsenic to form n-type semiconductors. We can watch this through this video. Here, instead of silicon atom, we replace arsenic, which belongs to group 5. You can see that arsenic contains 5 electrons. All the 4 electrons form covalent bonds with the nearby silicon atoms, and there is no chance for the free electrons to make a bond. As a result, when doped in one arsenic atom, one additional free electron will be added to the silicon. So, you know, silicon atom consists of then free electrons. When we add one arsenic atom, one negatively charged free electron will be there. If we add thousands of arsenic atoms, thousands of negatively charged free electrons will be there. If we add billions of arsenic atoms, billions of negatively charged free electrons will be there. That means by doping group 5 phosphorus or arsenic, we can form negatively charged semiconductors. They are called as n-type semiconductors. So, my dear children, as we studied so far, the conductivity of extrinsic semiconductors is higher than that of the intrinsic semiconductors due to the presence of large number of holes and free electrons. You can remember, p-type semiconductors consist of large number of positive holes. N-type semiconductors consist of large number of negative free electrons. So then we can focus our attention on the contribution of holes for the conductivity of p-type semiconductors. Here, when supplying a current through a circuit, external circuit, positive, negative, this is the cell, what will happen? You can see arrowhead represents the direction of diffusion of holes. Here, when change in the terminals of the cell, conduction of electricity occurs by the diffusion of holes. You can see the diffusion of holes. Here, contribution of free electrons for the conductivity of n-type semiconductors. Earlier we learned about contribution of holes for the conductivity of p-type semiconductors. Then the contribution of free electrons for the conductivity of n-type semiconductors. You can see when supplying a current through a circuit externally, conduction of electricity occurs by the diffusion of free electrons. Here free electrons diffuse from negative terminal to the right, like this. The arrowhead represents the diffusion of free electrons. So when change in the terminals of the cell, conduction of electricity occurs by the diffusion of free electrons. This shows the conduction of electricity, because you have to remember that conduction of electricity occurs to the opposite direction of the conduction of free electrons. Now, my dear children, let's focus our attention on the p-n junction. What is called as p-n junction? So far we studied about p-type semiconductors, n-type semiconductors. Then we are going to study what is meant by a p-n junction. Right. A p-n junction is made by reverting a p-type semiconductor to a n-type semiconductor in a special manner. All right. Let's watch the formation of p-n junction. Here, as you can see, first of all we take a p portion, n portion, we revert in a special manner. So free electrons diffuse to the p side and holes diffuse to the n side, formation of obstacle here, charge barrier. The other electrons will not be able to move to the p side and holes will not be able to move to the n side. So the obstacle or the charge barrier takes place, forms in between the p-n junction is called as depletion layer. This is called as depletion layer, right. It acts as an obstacle for the flow of other electrons and holes, right. How to make a diode? It's a very important appliance that we used in the electronic appliances. When connecting two conductor terminals to either sides, as you can see, this is the p-n junction. Here, two conductor terminals are connected to the either side of the p-n junction. So it is called as the diode, or we can say junction diode. When connecting two conductor terminals to either sides of a p-n junction, a junction diode is made, right. So then we have to understand two different concepts. For the function of the diode, we can forward bias the diode and also we can reverse bias the diode. You have heard about forward biasing, reverse biasing, right. Forward biasing and reverse biasing of a diode, right. As you can see in this video, you can watch p-type semiconductors consist of large number of holes, positively charged holes. Similarly, n-type consists of large number of negatively charged free electrons. This is the p-n junction. Free holes, positively charged, free electrons, negatively charged. The center of the p-n junction is called as depletion layer. Here, what happens? As soon as the junction is made, as we learned earlier, free electrons diffuse from n side to p side and positive holes diffuse from p side to n side. So, when supplying external potential difference through a dry cell, positive terminal to p side, negative terminal to n side, what happens? The positive terminal of the dry cell repels the p-type holes. Negative terminal repels free electrons. As you know that like charges repel each other. As a result of this repulsion, the depletion layer narrows, or the space region around the p-n junction narrows. As a result, flow of current takes place through this p-n junction diode from p-type to n-type. You can see the diffusion of free electrons from n side to p side, holes from p-type to n-type. So, reverse bias. Reverse biasing means what? We connect negative terminal to the p side, positive terminal to the n side. As you know, unlike charges attract each other. So, the negative terminal attract the holes towards itself, positive terminal attract the electrons towards itself. As a result, the depletion layer becomes broadened. When the depletion layer broadens up, no flow of charges takes place from p side and n side. Right, you can see that depletion layer broadens, no flow of charges takes place. This condition is called as reverse biasing of p-n junction. In that case, current or electricity does not flow through the p-n junction. Right. Let's move to another video to understand forward biasing instance of the p-n junction. Positive terminal to p side, negative terminal of the dry cell to n side. You can watch the movement of free electrons from negative to p side and flow of current from p side to the n-type. So, when we switch off, what happens? Again, the depletion layer will be formed here. Now, again, if we connect the switch, the flow of current takes place. Right. Then, my dear children, we have to pay our attention on the types of diodes. This is also an example for a diode. This is a very small electric appliance. We used diode. You can watch that. The diode consists of p side and n side. All right. Now we have to understand the picture of the diode, the symbol of the diode, and also the parts of the diode clearly. Anode and cathode of a diode. As you can see, this picture gives you the anode and the cathode. The black color parts relevant to the anode, the silver line relevant to the cathode. This is the symbol of the diode. The diode symbol contains an arrow and straight line here. The arrow begins from the anode. Arrow head is pointed towards the cathode. You have to clearly understand this is the anode of the symbol of the diode. This is the cathode or negative or N part of the symbol of the diode. Right. Now, let us see this, the function of the diode. I am going to show you a simple activity. Before the activity, you can watch that when change in the terminal, bulb glows. When change in the terminal, again bulb goes out. That means we have to understand a diode is an electrical device which allows the electricity to flow only in one direction. My dear children, I have used a diode here. This is a dry cell. This is a bulb. There is a gap between the circuit. I am going to place the diode here. You can see bulb does not glow. When I put the positive terminal of the diode to the negative terminal of the dry cell and negative terminal of the diode to the positive terminal of the dry cell, the bulb does not glow. Then it means electricity does not flow from negative to positive or cathode to anode through a diode. Now you can see very clearly, I am going to change the terminals of the diode. Now you can see that bulb glows. You can see that bulb glows. The bulb glows because of the flow of electricity through the diode. Now I am going to use another LED here, because you know you will learn in coming lessons LED is also a diode. Here negative to positive, bulb does not glow, but positive to positive, here LED glows properly. What does that mean? Current flows through a diode only in one direction. One direction means when the diode is in forward bias condition, electricity flows through it. In that case, we have to keep in mind positive terminal of the dry cell should be connected to the anode of the diode and negative terminal of the dry cell should be connected to the cathode of the diode. Right. We can use the diode as a switch. Here you can watch that when we connect the positive terminal to P side or positive, negative terminal to the N side or negative, current flows through the diode, current flows in the direction of arrowhead, bulb glows. So this is like a closed switch. So diode can be used as a closed switch. When you think about the next diagram, you can watch that negative terminal of the dry cell to the positive terminal or anode, positive terminal to the N side or cathode, current does not flow, bulb does not glow. So that means a diode can be used as an open switch or disconnected circuit. Right. Through this you can see the function of diode. Here current flows, here current does not flow because positive to negative doesn't flow, positive to positive current flows. Through this, what can we understand? A diode is an appliance which allows the electricity to flow only in one direction. A diode allows the electricity to flow only in one direction. Right. Then we have to focus our attention on the uses of diodes. Where we use diodes, my dear children? Many electronic components need a DC for their operations, but domestic power supply we obtain from the national grid consists of AC current. Domestic power supply, dynamos and generators produce AC current. AC means alternating current. DC means direct current. A diode is used to convert an alternating current into a DC current. Here you can understand the difference between DC current and AC current. The current in which the direction does not change with time is called as DC current. Here flow of electrons from negative to positive, current flows from positive to negative. This shows a DC current. This is the DC source. DC means we have used a dry cell here. Load, we can use a bulb or whatever the appliance here. Current always flow from positive terminal to negative terminal. This is the direct current. Then what is meant by AC current? Alternating current. As you can see, alternating current, here the direction changes. If we represent in a graph like this, you can understand that in sometimes voltage becomes positive, sometimes voltage becomes negative. Now we can compare the directions of DC and AC. Here DC current flows always from positive to negative terminal, but AC current, we use the symbol for the AC current, it alternates the direction. AC current always alternates the direction. Normally the direction of the AC current that we use in our houses alternates 50 times per second. Right. I am going to show you a simple activity to find out that one using the galvanometer. Here I have used a battery. Now you can watch that, my dear children. When I connect that, what happens? The galvanometer indicator deflects right there. Again you can watch that. It is in the center zero galvanometer. It deflects to right. Now if I change the terminals here, what happens? Terminals of the dry cell, you can watch that it deflects to left side here. That means current flows from positive to negative, only one direction. Now let's focus about the AC current. This is the structure of the dynamo. The dynamo produces an alternating current. Let's learn how does it vary. Here you can watch the galvanometer indicator. Okay, when connecting a dynamo to the center zero galvanometer, you can watch that indicator deflects to either side. What does that mean? Dynamo produces an AC current. That is why it deflects to the either sides. Right. Then you can represent the variation of the voltage over time using the graph like this. Direct current we represent using a straight line. AC current we represent like this. It is a wavy line. Right. This is center zero galvanometer. Center zero galvanometer is used to identify the direction of the flow of current. Right. My dear children, you observe that when connecting an AC current to a galvanometer, indicator deflects to either sides. You could observe that. Similarly, when connecting a DC current to a galvanometer, instead of AC, galvanometer deflects right. And also, when changing the terminals of the cell, you could observe that the galvanometer deflects to left. Alright, this is the end of today's program. In coming programs, I am going to teach you how to convert an AC current into DC current. So my dear children, you can refer to the textbooks and also answer previous question papers. At the same time, if you have further doubts, for the further clarifications, you can get the support from your class teacher. And if you want, you can watch this program again through channel NIE YouTube. Have a nice day.